Okay, you see, today I am going to talk about the origin of degeneracy. It's a very interesting concept. Now, when do we talk about degenerate matter? Of course, for a given temperature, you see, we talk about degenerate matter only when the density is very high. So, degenerate matter we talk about only for given temperature when the density is very high. Okay, so high that the well-known equation of state. What I mean to say is that in this case the well-known equation of state, which is basically PV is equal to nRT, this is no longer valid, and then we have to talk about a different equation of state, and this is what we are going to talk about. And why does this happen? So the question is why this breaks down, why ideal gas law breaks down. Now you have to understand that this ideal gas law is basically for the classical particles, right, which are distinguishable. Okay, however, what we are dealing with are electrons, protons and neutrons in the atom. Okay, in the stars you will see that during the course of stellar evolution, the electrons and later on the neutrons play a very crucial role. Now both of these are what type of particles? Are they bosons? Of course not. They are fermions, right? Now there lies the reason for the breaking of the ideal gas law. You see, when the density is very low, so that the de Broglie wavelength is much smaller than the distance between two particles, then we can talk about the classical behavior. But when the distance between them becomes closer to the de Broglie wavelength, then we have to talk about quantum particles. Quantum behavior starts manifestation. Now the very fact that they are fermions then starts becoming important. And how do they become important? You see, for fermions we know that there is a very important rule. And what is that? It is Pauli's exclusion principle. Right, no two fermions can remain in the same quantum state. And because of this, so what happens is that this Pauli's exclusion principle starts becoming important when the distance becomes closer to the de Broglie wavelength. Distance between them, separation between the particles. This I have already talked about in a separate lecture, you will see. And today I am going to talk about what happens because of the Pauli's exclusion principle. Okay, so as I was saying, for high densities, this Pauli's exclusion principle, let me talk about it as PEP. So IGL is for ideal gas law and PEP is Pauli's exclusion principle. Now this is basically a manifestation of the quantum behavior of particles, right? So quantum behavior, which means for fermions we have the Pauli's exclusion principle. So what happens at high densities? The quantum behavior starts manifesting, it becomes important, and as a result the Pauli's exclusion principle becomes important for the relation between pressure, density and temperature. So when we have classical behavior, then we have a different relationship between, you see, density, temperature. So we have a different EOS. But in the quantum regime, I am talking about fermions right now, you see, it changes. The way the equation of state changes, and the reason is the Pauli's exclusion principle. Okay, now let me little bit talk more details about the Pauli's exclusion principle. Well, of course, in details, what is Pauli's exclusion principle? Well, Pauli noted that particles with spin half, that means half of n, where n is a odd number, right, they follow different statistics. And what statistics is that? It is basically Fermi-Dirac statistics, and such particles are called Fermi particles. So what does Pauli's exclusion principle state? Basically it states that there cannot be two or more Fermi particles with all equal quantum numbers in a single cell. So our Pauli's exclusion principle is no two Fermi particles, right? So no two, this is not number, this is no two Fermi particles with all equal quantum numbers in one quantum cell, right? Now this applies, as I was saying, not only to electrons but protons, neutrons, but this doesn't apply to particles having integral spin. Say for example the helium nuclei, right? It has a nuclear spin 0, so it will not apply to that. Now what is the quantum cell I am talking about? Well, basically the quantum cell which I have defined here is defined in phase space, that is in the 6-dimensional space of geometrical space x, y, z, and momentum space px, py, and pz. Now for a quantum cell, the volume element in phase space is then given by this value, delta x, delta y, delta z into delta px, delta py into delta pz is equal to h cube. This is equation 1. What is h? H is Planck's constant. Now you see the number of elements in this quantum cell can be at most 2. These 2 electrons must have opposite spin directions. Then only we will not violate the Pauli's exclusion principle, right? So there can be only at most 2 electrons in a quantum cell. And why 2? Because they must have opposite spin directions. Then only we will be following this rule. That means no 2 fermionic particles with all equal numbers in one quantum cell. Now let us look at the geometrical volume of 1 centimeter cube. Now for a quantum cell, so let us look at geometrical volume of 1 centimeter cube. Now you see, for a quantum cell we have what happens. So because of this I am already saying delta x, delta y, and delta z is equal to 1 centimeter cube, right? So as a result of this we have delta px, delta py, and delta pz is equal to h cube, right? Since now these are equal to 1. Okay. Now, and in this momentum state there can be again at most 2 electrons. So at most 2 electrons with opposite spins, right? Fine. Okay. Now you see, for the electrons in this 1 centimeter cube volume, let us plot in the momentum space all the arrows for a given absolute value of momentum P between P and P plus dP. Here, like this. So what I have done is, for electrons in 1 centimeter cube, I have just plotted, right, in momentum space, P space, all arrows for a given absolute value of momentum between P and P plus delta P. Okay. Now you see, what do you see? Well, all these arrows end in a spherical shell with radius P, and the thickness of the shell is delta P. Okay. Then what about the number of quantum cells corresponding to these momenta between P and P plus delta P? So the number of quantum cells corresponding to momenta between P and P plus delta P is how much? This is just equal to, you see, 4 pi P square delta P divided by H cube. Right? Okay. So volume of the shell divided by H cube. Now, what about, so this is just the number of quantum cells. Okay. Now, what about the number of electrons per centimeter cube? You see, now what about the number of electrons per centimeter cube which have momentum between P and P plus delta P? What about them? Well, you see, this number of electrons, let us write like this: momentum between P and P plus delta P. This can at most be, yes. Why 2? Because electron has 2 spins, right? Positive spin and negative spin. We can have 2 electrons in a single quantum cell. And this is equal to 8 pi P square delta P by H cube. And this is basically 8 pi, let me break it down, me cube V square delta V divided by H cube. What is me? Me is basically the electron mass, right? Now, since I have now broken down P is equal to me into V, so this is basically corresponds to the velocity distribution. Okay, so now what can you see here? What do you see here? You see, basically what I am seeing is basically that the number of electrons P delta P, right, basically it must be less than some number Ne max. This is what I am seeing. Again, P plus delta P. And what is the value of Ne max? This value here. And so basically Ne max, you see, this is equal to some constant K into VQ into V square. What is this K? This K is basically 8 pi Me cube delta V divided by H cube. Okay, so this is what I am observing. This is our result. Now let me write it down clearly. Yes, so basically we are getting this result. Number of electrons must be less than Ne max, which is proportional to V square. So what does it mean? Okay, so this is what I was saying, you see. So in the previous section we have just tried to find the number of electrons per centimeter cube having momentum between p and p plus delta p, and then using this relationship we write down the velocity distribution and we observe this thing, right? So number of electrons must be less than equal to the NE max, and what is this values? Equal to some constant into v square. So this means that in the NE versus v plot we will have a parabola, something like this, and this is basically because of Pauli's exclusion principle. So this means that this very existence of red line here is because for fermions only. So this is for fermions, right? Now you see what happens. Let us compare this with that of the Maxwell-Boltzmann distribution. Okay. Now the Maxwell-Boltzmann velocity distribution to be on equal footing. Let us compare with that, which also gives us the number of electrons per centimeter cube having velocities between v and v plus delta v. And what is the relationship? Well, here. So this is our value of number of electrons per centimeter cube having velocities between v and v plus dv, and this follows from the Maxwell-Boltzmann distribution. Now we do know that this is correct only as long as the condition before, which condition? This condition. So this is valid unless this condition, say condition A. Okay, so this Maxwell-Boltzmann distribution is valid when number of electrons is small enough so that condition A is satisfied. No, right? Yes. So what did I say? What I am saying is that this follows from Maxwell-Boltzmann distribution, and as long as we do not violate the condition A, then we are good to use this. However, for very high electron densities, the Maxwell-Boltzmann distribution may give us much larger values of NE, right, which than what has been permitted by the Pauli's principle. So basically this relationship here is a manifestation of the Pauli's exclusion principle. Here I have written down the Pauli's principle like this, and what I am telling you right now is that if we have a very large number, okay, then this condition will be violated. So what will happen? Let us see here. Okay, so suppose let us plot the Maxwell-Boltzmann distribution for an electron density of Ne is equal to 1.5 into 10 to the power 23 per centimeter cube, and also temperature is 10 to the power 5 Kelvin. Let us also plot here the maximum possible number of electrons per centimeter cube for a given velocity. Here I have plotted this. Now let me show you how the plot looks like for the Maxwell-Boltzmann case. Okay, so here I have shown you the plot for the Maxwell case as well. This should be little bit, yeah, like this. Okay. Now what do we observe? basically what we observe is that for this particular case, right, for these values, and also looking at the Pauli's exclusion principle, the any value, we see that there are no more electrons on this side, right? No more electrons with a given velocity 1 centimeter cube than what has been permitted by the Pauli's exclusion principle, right? Now let me again do a different plot. Okay, so what I am going to do, I have shown you the values for T is equal to 10 to the power 5 Kelvin, right? And density is 1.5 into 10 to the power 23 per centimeter cube. Okay, now this time let me double the electron density here, but the temperature remains the same. So this time let the density be Ne is equal to 3 into 10 to the power 23 per centimeter cube, and the temperature be the same, 10 to the power 5 Kelvin. So what do the two plots look like this time? Okay, here, so this is the plot. Now did you see any difference? So this is, you see the Ne max, the previous case, and this was the previous value. You see here the values. So this is the Maxwell value, right? This one here, and this is the Pauli's value, Ne max. Now what is happening? Let me again compare to the previous sheet. So here what was happening is that Maxwell value, the electrons, number of electrons, they never crossed over to this side. However, if I increase the density but the temperature remains the same, you see from the Maxwell's distribution you will find some electrons which are on this part, right? So for this particular density, twice the density, the Maxwell distribution gives us more electrons per centimeter cube with a given velocity. These ones here, these ones, than are permitted by Pauli's principle. What I mean to say, these electrons are not permitted by Pauli's principle, right? Now these electrons then cannot have such low velocities. Here it is not possible, and they must acquire higher energies than given by the Maxwell distribution. So what will happen? What can we do? We can only squeeze that many electrons into 1 centimeter cube if this additional energy is supplied. Now if the electrons in this cross hatched area obtain the lowest possible energies, then they will appear in the shaded area here. Okay, and the area of this shaded area must also be just as large as the crossed hatched area in order to accumulate all the electrons which are not permitted to be in the cross-sectional area. So what is happening is that here these electrons, they are not permitted by the Pauli's exclusion principle, though they will be accommodated in this part. This is what is happening right now. Okay, so if the electrons in this cross-sectional area obtain the lowest possible energies, they will appear in the shaded area. And as I was saying, that this must have the same, should be as same, but mean the same area as this, so that so that we can accumulate all the electrons which are not permitted to be in the cross-hatched area. Now the actual momentum distribution obtained from this density is shown here by the heavy line. here, actual distribution. It is shown by the heavy line over here. You can see. Now, up to a certain momentum P0, which is known as the Fermi momentum, the distribution follows the maximum possible number of electrons NQ here. Now, there is also a fraction of high energy electrons which still follows the Maxwell distribution in the so-called Maxwellian tail here also, right here, Maxwellian tail. Now the gas considered here, what should we call it? We should call it partially degenerate because the Maxwell tail is still rather extended, right? So instead of having a distribution like this, we are having a distribution like this, you see. So this one is somewhat degenerate and this one is somewhat Maxwell. So we have both cases here. Okay. Now what happens if the electron density is increased further? Then you see the shaded area will grow much more and a large number of electrons have to acquire high energies. So P0 grows and Maxwell's tail shrink over here. Now if the Maxwellian tail contains basically a negligible number of electrons, then we can talk about complete electron degeneracy. So as I am saying, if the Maxwell tail, it contains a negligible number of electrons, then we talk about complete electron degeneracy. Okay, now you see in this previous figure here, we have also plotted the Maxwell's energy distribution for the same here, for the same number density, but at a higher temperature. The temperature is higher. The number density is the same, temperature is 3 times higher. Now you see, for the higher temperature, all the electrons, they obtain higher energies, and the number of electrons with a given velocity, according to the Maxwell velocity distribution, they never exceed the number permitted by the Pauli's principle. There is something very interesting also. Note that this change, this distribution, this plot, this never depends on the temperature. Now for this temperature here, the gas with Ne is equal to 3 into 10 to the power 23 per centimeter cube is not degenerate, even though here, let me talk about this case. Now, as I am saying, for this temperature, the gas is not degenerate, even though the temperature was at 10 to the power 5 Kelvin. So, you can say for a given Ne or number density, there is always a temperature by which the degeneracy can be removed. So you can say at that time previously there was somewhat degenerate, but if we increase the temperature, if given the same density, the degeneracy has been removed. There is no such condition. Okay. Now if the temperature is high enough, the number of electrons given by the Maxwell velocity distribution will always stay below the number 2NQ. So if such a thing happens, then we will not talk about Fermi distribution, or the Pauli's exclusion principles effect will never come here. We will not come into the picture, right? And we are good to go. So everything is okay if you see the number is less than 2nq. The moment it starts becoming equal is this region over here, and then we have to put the electrons in the higher momentum region, and that causes a different distribution. Then we can say the electrons start becoming degenerate. Now let us look at the situation for protons and neutrons. Now will they also be, so let us look for protons or neutrons. So the question is, will they also be degenerate if the electrons are degenerate? Now you see the maximum number Nn of neutrons with momentum between p and p plus delta p is again given by the previous relationship. Here the condition, this one over here, right? Now with p is equal to mn into v, right, and mn v square average is equal to me v square average for equal temperature in a non-degenerate gas. What do we find is that V average is proportional to 1 by root over mn, and also P average is proportional to mn. So for neutrons the momenta are all larger, and therefore the number of quantum cells in the momentum space is much greater for the heavier particles. Right. So result is that the number of quantum cells in momentum space is much greater for heavy particles. Now according to this equation, condition A, which is basically condition A, according to this here, the permitted number of particles with given velocity increases, right? We can write like this: neutron divided by now this is, you see, proportional to mn by me whole cube. Of course, for low velocities, the number of particles with given v according to the Maxwell distribution increases only proportional to m to the power 3 by 2. Okay. Now look at the picture over here, where we have plotted the Maxwell-Boltzmann velocity distribution for the number of neutrons, right? So this is basically for the neutrons, which is equal to 3 into 10 to the power 23 per centimeter cube, and also the velocity distribution according to the previous equation, the restriction, the velocity, that means the Pauli's restriction over here. Now for this number of particles per centimeter cube, what we find is that we also found the degeneracy for electrons, while the number of neutrons stays well low below the Pauli's principle limit for all velocities. What I want to say is this thing: you compare this picture with the picture over here, right? This picture here, the temperature 3 into 10 to the power 5 Kelvin and density is this. Now you compare this with this here. You see, what do you observe? So basically we observe is this: for the same number density we find that the degeneracy for electrons, while the number of the neutrons stay well below the number of neutrons, it is staying much below the Pauli's principal limit for all velocities, right? The velocities are basically lower by a factor of 100. Now, because of the higher masses and larger momenta, we can have more higher particle densities for protons and neutrons, in fact by a factor of 10 to the power 5, before they can become degenerate. This is important. So, we can still have more density, more particle fitting of the order of 10 to the power 5 more, so that this condition is reached, so that this plot comes closer to this plot, and we can say that the neutron or gas has started becoming degenerate. Of course, in the dense helium core we do not have protons or neutrons, and helium does not obey the Pauli principle. The alpha particles do not degenerate, only the electrons in the helium core are degenerate. Okay, now before I finish, let me again tell you one very important thing. Here, this value, when I was discussing this plot, remember, so the electrons which cannot remain in this area has to be accommodated over here, and as a result the maximum momentum here, this is known as Fermi momentum, up to which the electrons has to be accommodated. Fine. So we have very nicely discussed about the electron K density for this temperature, density 3 into 10 to the power 23, temperature 10 to the power 5 Kelvin. Next we did the same for we did the same for a different case over here, right, for a little bit higher case also, and this I have also shown you in this plot as well. So we have discussed about two different sets. Now, to make matters even more interesting, and also to further discuss the effect of the reason for the fact that the temperature is not in the picture anymore when the gas becomes degenerate, let me discuss 2 or 3 more examples, and then you will understand why this is happening. Okay, so here in this plot, you see I have taken the same density, this time a different density of 6 into 10 to the power 27 per centimeter cube. However, what I am doing is that I am now slowly decreasing the temperature. Okay, so let me first talk about this high temperature case. So density remains fixed at 6 into 10 to the power 27 per centimeter cube, and the temperature is very high, 2 into 10 to the power 7 Kelvin. Now what happens in this case, the momentum distribution here, the momentum distribution, now this one, the black, the solid line one, corresponds to the Fermi distribution, right? Okay, and you see it nearly coincides with that of the Maxwell-Boltzmann distribution, which is shown by the dotted line. Now this time I am showing you the exact Fermi Dirac distribution, which I didn't show you last time, to show you a better picture. Now, okay, so this is case 1, right? Now what happens? So what is happening right now is that none of the quantum states here, this is the limit, this is the here, this line, this is the NE max, this line over here, right? This is the NE max. Remember this. So what is happening is that none of the quantum states are fully occupied, and the electrons behave as classical particles. So these are classical. No problem. Okay. Now let us decrease the temperature to 2 into 10 to the power 6 Kelvin. So this is case 2, the red ones. Now as the temperature is decreased here, what is happening is that the Maxwell-Boltzmann distribution peak. This is the red one, actual Maxwell-Boltzmann distribution. Now you see, these many electrons, they are not at all. So this number of electrons are not permitted. Electrons not permitted, right? So where will they go? They will move to this side. No, not this one. Yeah. So these many electrons here, they are basically moving to this side of the red part. So in the red part, you see. So what has happened is that as we have decreased the temperature, the peak in the Maxwell-Boltzmann distribution has shifted to smaller momentum value and is also higher. Right. Now the number of electrons with small values of P expected from classical values, they are exceeding, as I was saying, the maximum allowed by Pauli's exclusion principle. So these electrons are forced to assume quantum states here with higher momentum. You see, this is lower momentum. See the low momentum values, they are increasing. So Maxwell-Boltzmann momentum was small, but they are not permitted. So they are being shifted over here. So basically they are shifted to higher momentum values. So we have basically the electrons are shifted to assume quantum states with higher momentum. And as a result, there is a shift in the peak. This is the real peak. Okay. So the peak in the distribution occurs at higher momentum value. Now due to the higher momentum and velocities of these electrons, the red plot I am talking about, the electron gas exerts a higher pressure than it would be if it was a classical gas. So if it was a classical gas, then this would be the pressure. Now pressure would be much lower from these many electrons. You see, the average is around here. But since it has been shifted due to Pauli's principle, the overall pressure is much higher. And so, due to the higher momentum and velocities of these electrons, the electron gas exerts a higher pressure than that was if it followed the classical physics. Now this is the degeneracy pressure. This is classical pressure upon following the Maxwell-Boltzmann distribution, but this is just because of the Pauli's principle. So we have a new origin of pressure, right? This is known as degeneracy pressure. Now what happens if we further increase the temperature? So first 2 into 10 to the power 7 Kelvin, next to this part. Now it is important to note that here the gas is somewhat classical as well. Also here this part, and also there is a quantum degenerate part as well. So there is a partial degenerate gas. Now if we further increase the temperature, say the blue line, so the temperature is decreased. Yes, if the temperature is further decreased, what happens? Now you see, if it was a Maxwell-Boltzmann distribution, it used to be the case. But you see that all these electrons are not at all permitted. So where will this go? They will go to this side of the line. This line. They will go all over to this side. Over here. Right? So as the temperature is decreased even more, the blue lines I am talking about, 2 into 10 to the power 5 Kelvin, the lowest momentum tails become nearly all filled up here. Right. And right now what is happening is that number of electrons, they are following exactly the NE max. This value. They are following the NE max. Right. Until it sharply drops. Now in this state of strong degeneracy, further decreasing, if I decrease to say 2 into 10 to the power 3 Kelvin, what will happen? This case, blue line, nothing will happen, because you see, very important, the tail, this tail nature, there is a curve. This curve is due to the Maxwellian reason. Now if I decrease the temperature even more, so if this was case 3 and this was case 4, what will happen is more and more gases will be on this side. But as a result, all have to be accumulated over here, and this steep graph, nothing will change. So in the case of stronger degeneracy, further decrease of temperature hardly changes the momentum distribution, and as a result the electron pressure, this becomes nearly independent of temperature. Okay, so what is happening, you can say, is that slowly, initially it was like this, slowly it becomes like this. No, it is not like this, it should be like something like this, and after some time they all become here, this part, there will be no shifting. This is what I mean to say. Further decrease of temperature here, further decreasing of temperature will hardly change the momentum distribution, so that electron pressure now becomes nearly independent of temperature. Okay, now let me show you a different graph over here. So this time, as I was saying, I am showing you the T is equal to 0 Kelvin scenario, right? So I am showing you the two distributions for two different densities. One is 6 into 10 to the power 7 and another is twice that value. Now what do you see? Basically we do not have anything over here Maxwellian, right? Because they are following Fermi Dirac statistics, and they are following, this time they all of them are following this any max distribution over here. This is just the Fermi Dirac statistics, and here all lowest available momenta are fully occupied. Now the blue line is for the same density, but for here the blue line is for the previous case over here, this one, the blue line, this was temperature for 2 into 10 to the power 5 Kelvin. Now if I decrease it to 0, you see there is a steep decrease. So this is what I mean to say, is that as we decrease the temperature, the degenerate gas pressure here becomes independent of the temperature, right? After becoming fully degenerate. Okay, now the red line here has twice the density. So what is happening? The same thing you see. And also this is the Fermi momentum, these values. Okay, so before I finish, let me talk about the importance of electron degeneracy in stars. Just a little bit. Why is it important? Well, you see, as a star or its core slowly contracts. I will talk about this later in our course during stellar evolution, but before that let me give you some flavor of it. Now as the star and its core, they contract, the density, they become so high that the electrons become degenerate and exert a much higher pressure than they would if they behave classically. So this is the thing. If they behave classically, this would be the pressure, but the density is high, so they must follow the Pauli's exclusion principle, being fermions, and as a result the pressure is higher. Now what happens, since in the limit of this strong degeneracy the pressure is no longer dependent on the temperature, what happens? This degeneracy pressure can hold the star up against gravity. Important fact is, regardless of the temperature. So a degenerate star does not have to be hot to be in hydrostatic equilibrium. This is important, right? So a degenerate star does not have to be hot to be in hydrostatic equilibrium, and it can remain in this state forever even when it cools down, even when it cools down, right? Now this is the case for the white dwarfs. The importance of relativity is that when a degenerate star becomes more compact and the density increases further, the pressure increases less steeply with density. Now this has important consequences for massive white dwarfs, and as we will see later in our course, that it implies that there is a maximum mass for which white dwarfs can exist, and that is the Chandrasekhar mass. Okay, so that's all for today.